Welcome to the Problems Channel Season 3, Episode 15, the episode which I titled A Single Pass Janus Sort for the reasons that will become evident shortly. And before we deep dive into the underlying mechanics of that sort, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the home page of this channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. We suggest that you watch that episode in its entirety and follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. The best way to ask your question is to find an episode of interest to you and use the comment section below that episode to ask your question, and I will do my best to find the time to answer all of your questions. And perhaps I do not say this enough, but I want to extend my special and deepest gratitude to the current subscribers and to the current supporters of this channel, especially those people whom I know personally from Quora. Out of respect for your privacy, I will not call out your names in public, but you all know whom I mean. The objective of the challenge S3CS3 is to construct an algorithm that honors the following two constraints. The first constraint that the sought-after algorithm must honor is that this algorithm has to operate on the input linear container, otherwise known as an array, in a single pass. In other words, in the algorithm that we're looking for, we are only allowed to iterate over the input container in some fashion only once. The second requirement of the sought-after algorithm is that this algorithm has to perform its magic in place. And that means that according to the second requirement that we impose on the sought-after algorithm is the following: the space complexity of that algorithm must be big O of 1. We're not allowed to allocate any sizable chunks of memory in addition to what the current input linear container, otherwise known as an array, already occupies. And the technical essence of this algorithm has to amount to the following. On the input into this algorithm, the linear container, otherwise known as an array, contains only two distinct types of objects, zeros and ones. And that means that if a given element at a certain position in this input array is not 0, then it is 1. And conversely, if at a given position the contents of this input array is not 1, then it is 0. And of course, it should be understood that this particular problem is encoded in such a way that the proverbial zeros and ones simply represent any two distinct types of objects. The objects in the array could be, for example, tomatoes and cucumbers. They could be triangles and hexagons. It doesn't really matter. The proverbial zeros and ones are an abstraction, basically, for two distinct types of objects. And the objective of this algorithm is, in a single pass and in place, to sort these zeros and ones in such a way that the objects of one type, let's say zeros, gravitate towards one extremity of the input array. Let's say all the zeros have to be placed on the left side of the input array, and all the ones or the objects of the remaining type have to gravitate or bunch up towards the diametrically opposite side of the input container, or let's say ones in this case have to be placed on the right of the array. But again, this is an arbitrary requirement. You can exercise a different choice. For example, you can bunch up and pile up all the ones on the left of the array, and conversely all the zeros on the right of the array. For demonstration purposes, we will put zeros on the left and all the ones on the right. And the definition of all is that after our single pass in place algorithm is done with the input array, then the objects in this array have to be sorted in such a way that there are no intervening elements of the other type in between the elements of this type. For example, in the midst of zeros over here as a sample demonstration, there should not be a single one. In other words, contiguously, all zeros must follow one another. And likewise, among the multitude of ones, there cannot be any intervening objects of the remaining type. There cannot be any zeros. And again, contiguously, all the ones have to form a block of memory that contains only ones. And in some sense, that is what you saw in the thumbnail for this episode right here. I placed Janus. This is where the name of this sort came from, because after that particular sort is done, this is precisely what we will have. We will have a logical separation between zeros and ones, and this is where I injected the this particular creature, let's say, that has two faces and looks into mutually exclusive or diametrically opposite directions. The gaze in one direction signifies all ones, and the gaze of that thingy in the other direction signifies all zeros. And if you have a better name for that sorting algorithm, then by all means enlighten us. Maybe there is even a dedicated name by now in computer science for this specific type of problems. Let us know in the comment section. Now, one word of caution over here is that people who have been writing, for example, the C code for a living for many decades, as I did, they tend to come up with the following solution. They will say, Roman, what's wrong with rolling through the input container once, and then as we iterate over the input array, we count the number of ones, and we do not even have to count the number of zeros, because the number of zeros will be known automatically if, let's say, x is the number of ones, and then n is the size of the input array, then what is the number of zeros once we roll through this container once? Well, n minus x will be the number of zeros. And once we know the number of ones and once we know the number of zeros, what some people propose, and in the back of my mind I also have this idea, we use the C runtime library function called memset. Memset on the array set this from the beginning of this array, we set the contents to 0 for how long? Well, it will be n minus x times size of int. that many, that long block of memory will be set to 1, and then a plus n minus x, the number of zeros past it, we will set it to 1, to that many. Set it to 1 for x element times size of int. But there are two problems with this memset approach. First of all, it's a hack. Technically, let's call it what it is. It is a hack. And once we roll through this input container once and count the number of ones and the number of zeros, this is one pass. This is one pass we do. But our favorite memset function, or actually we will have two memset functions over here. One to set all the zeros, and the second one to set all the ones. It's basically a syntactic sugar that hides or camouflages the second iteration through the container. So nitpicking a little bit on the way this approach works, this approach actually violates the single pass requirement that we impose on this algorithm. But this is just smaller potatoes. Fundamentally, this is a hack. This is not an algorithmic solution. And in this problem, we're looking precisely for a solution that is algorithmic, that is based on a beautiful idea that can actually be used and reused elsewhere in other algorithms. Remember that on this channel, during season 1 and season 2, we studied a number of problem-solving approaches in a dedicated manner. And in mathematics, in plain English, what is a problem-solving approach? A problem-solving approach in mathematics is basically a reusable heuristic template that can be lifted, shifted, carried over, and dropped from one context into another with equal amount of success or failure. As such, in this particular challenge, this is precisely what we're looking for. We're looking for a reusable and quite beautiful idea that conveys to the world that right now we're wearing a hat that reads a computer science oriented thinker. And in order to hone in on such a solution, we discuss two hints. As the first hint that may help you hone in on an intended solution of the problem S3CS3, consider the problem of detecting whether an input string is a palindrome or not. Before we deep dive into the discussion of the solution of this problem or the intended solution of this problem, I would like to make the comment that according to my personal and this time professional experience, unfortunately, most people in the industry who do the so-called computer programming are not really computer programmers. They should not be doing what they're doing. They should be doing something else, because these people not only do not understand what the computer science is, they do not really understand what the computer programming is. Leaving these people aside, among those people who do understand what computer science is and what computer programming is, eventually over time, and unfortunately, these people tend to either not distinguish the two or mix the two in a frivolous way. Meanwhile, there is a big difference between computer science and computer programming. And for example, one person can be a very strong and confident computer scientist and quite miserable computer programmer, and conversely, a person can be a very strong and confident computer programmer, but that person can be a very poor computer scientist. And on a very, very rare occasion, one person can combine both trends in just one person and be a very strong and confident computer scientist and a strong and confident computer programmer. And amongst all the people, this type of people are the folks who understand very well that a computer science algorithm is an entity, or as an abstract entity is quite separate from an implementation of that algorithm in a specific computer programming language of choice, and the two things are quite different. In some sense, a computer science algorithm is basically a finite description of how a given problem can be solved, and the idea here is that that description can be that description is so host computer programming language agnostic that it can be converted into pretty much any computer programming language, which of course supports that particular computational model. As such, in this episode, when you will see my ideas about an implementation of a particular algorithm, it should be of course understood that I use the best computer programming language of all times, C, just to convey my computer sciencey thoughts for the sake of being practical. Also, you can copy this code, compile it, run it, test it, and play with it. As such, with this understanding, with the laying out of common ground, and with this understanding out of the way, here is one way to detect if the input string, which is basically an array of characters, let's say ASCII characters, is a palindrome or not. And as a refresher, a palindrome is a linear structure that is symmetrical in its content with respect to its middle. For example, the phrase that you just saw a second ago in the opening image of this segment, no lemon, no melon, is precisely that, is a palindrome, and in plain English it reads left to right, and the same way it reads right to left. And in a slightly more computer sciencey and somewhat mathematically oriented language, a palindrome is a linear container such that when reversed and compared with the original will yield the result, yes, identical. And not a palindrome will yield the result of no, not identical. For example, A, B, C, D is evidently, as an input string, is not a palindrome, but if we were to tack on to the end of the string, for example, C, B, A as extra characters, then that string with that array will become a palindrome. And again, with respect to its vertical axis of symmetry, that technically speaking cuts the input array into equally sized halves, regardless of the parity of the size of the array, even or odd. And then with respect to that middle, we compare the equidistant elements of this array one by one, and these elements must be identical and they must match. As such, as a single pass and space complexity big O of one algorithm that will help you solve the problem S3CS3 correctly in an intended way, here's the fundamental, beautiful, computer sciencey or algorithmic idea. Okay, you know what, let me do that one more time as a hint. For those of our viewers who watched the movie Jurassic Park, remember the tiny lecture that the Dr. Grant made to one of the characters in the movie when he explained how velociraptors hunt in packs. His basically point was that they coordinate their effort, that is important, and he finished this lecture by saying pretty much these words. And the other two velociraptors, you did not even know they were there. This is a hint. Put this video on pause, walk away, think about it, come back when you generate an idea and compare your idea to ours. So here, a quite portable and beautiful algorithmic idea, which will put you on the right track. We introduce, in order to determine if the input string or the input array is a palindrome or not, we introduce two runners. One runner we will call the left runner, and the other runner we will call the right runner. The left runner traverses the input string in the rightward direction, and the right runner traverses the input container in the leftward direction. And in this particular case, it is important how they do it. The way they do it is encoded over here, but we'll come back to that idea in a second. Now, we position the left runner in such a way that the left runner looks at the very beginning, the logical beginning of the container or the element at position 0 in the array. Uppercase A sub 0, for example, we can say if we were to come up with some abstract notation that is computer programming language agnostic, we may introduce this notation array sub 0. This is the initial starting point of the left runner. So we will say he, let's say, points this way. The right runner, on the other hand, is positioned towards the last, logically last entry in the container. And in terms of the positions within the array, n-1 left, I call it index or left runner, right index or right runner. So the right runner is positioned against the rightmost element in the input array. And again, as you saw in the opening image for this segment, the two runners in this case, because whether a given array is a palindrome or not is the question that can be answered without modifying the structure of the input element. That is why here, for example, we will say that is a const char, a constant character pointer on the input, which means that we do not really have to modify the contents of the input array, and that is why the two runners, the left and the right, what you saw in the opening image for this segment, they communicate with each other using radio or walkie-talkie, and they communicate as follows. The left runner, for example, turns on the walkie-talkie and goes, runner right, how copy, come in. And to that, the right runner responds, runner left, this is runner right, I hear you loud and clear. Right now I see the character D, what do you see? To which the left runner replies, runner right, this is runner left, I see the character A. And at this point, the two realize that the character A, in this particular case, let's say A is not equal to D, and the game is over. We can go home, we can already make a decision that this particular string is not a palindrome. And that decision, that communication is encoded over here again, using the best programming language of all times. C, again, understanding that a computer science algorithm has nothing to do with its implementation in a particular host programming language of choice. These two entities are quite different, but again, for practical purposes, I encoded this part of the algorithm using the C programming language over here. If the character or the element in the input array that is seen by the left runner does not match the element in the array that is seen right now at the current position by the right runner, then at this point we already make a decision that this input container, the input array or the input string is not a palindrome. We return false. No, it's not a palindrome. However, if, let's say, our input string looks as follows, A, B, C, D, C, B, A. So at this point, our right runner is positioned against this character. And the two runners communicate with each other as I explained. The left runner goes, runner right, this is runner left, how copy, come in. The runner who runs from the right to the left replies, runner left, this is runner right. I hear you loud and clear. I right now see the character A. And the moment the left runner hears that, he goes runner right, this is runner left. I see the character A as well. Things are good. This if statement fails. And the code jumps over here, and look what's happening over here. This is quite interesting, and it is important for the intended solution of the problem S3CS3. Here again, the left runner advances right once, rightward once along the input array. In other words, the left runner steps rightward towards the logical end of the string, and at the same time the right runner steps left once by one position, advancing one position within the input container, but in the direction that is diametrically opposite to the direction in which the left runner advances through the input container, through the input string. In other words, the right runner steps leftward once towards the logical beginning of the input array. So now, for example, our left runner is positioned over here, our right runner is positioned over here, and now both again communicate, and they see that they both are looking at the character that is one and the same ASCII characters to keep things simple, and so we don't have to deal with the multi-byte, but it doesn't matter. Fundamentally, this is what it is. An object of this type called B and the object of this type also called B. Comparison, in this case, the if statement fails, both runners see exactly the same character that is again equidistant from the vertical axis of symmetry of the input string, and then both of the runners again execute the same maneuver. The left runner steps rightward once towards the logical or perceived end of the string, and the right runner steps left once towards the logical or the perceived beginning of the string or of the input array. This is encoded with left index plus plus and with the right index minus minus. If both runners see one and the same character, that is, each of which is equidistant, in other words, both runners agree on what they see for all equidistant pairs of characters with respect to the vertical logical axis of symmetry of the input string, then our loop will terminate. We will jump to this line of code over here, at which point we will return 1, which basically will signify yes. This input array is a palindrome, and we return. Again, look at this. Single pass, space complexity O, big O of 1. We did not really allocate any sizable chunks of memory to speak of. Technically, again, has nothing to do with the computer science algorithm, but all we have over here is 2 frame variables plus the implicit variables that the compiler will temporarily create when dealing with this line of code, but essentially this is what it is. Is this the only way to determine whether a given input string is a palindrome or not? Evidently not. Like I said before, the other way in which it is possible to determine if the given input string is a palindrome or not is to make a copy of the input string. In other words, if our input string is, let's say, A, B, C, D, we make a copy of the string, but then we reverse the characters in the second string, D, C, B, A, and then we roll through both containers. Now notice that when we will make a copy that contains the reverse string, the size of the string will be exactly the same as the size of the input string. The fact that we reverse the string does not really change its size, and now we roll through both containers again once and we compare. But this time we compare the characters in exactly the same position. I and I and I, whatever the current position is. On the first failure to agree on the characters that are seen at the current position, we short circuit, terminate the algorithm, and return 0 or false. The string is not a palindrome. But if our string were, for example, A, B, C, D, what is it? C, B, A over here, then the reverse string will be, again, the same thing. A, B, C, D, A, B, C, D, C, B, A. And if we roll through these two strings, then we will see that at each current position, but this time one and the same position, the characters match, and we will determine that our string is a palindrome. Of course, the drawback of this particular algorithm is what? The space complexity of this algorithm is no longer O of 1. It is actually O of n, because we need to allocate the chunk of memory that is equal to the size of the input string. But leaving this issue aside, the second honing in problem that we will solve, and that will help us solve the original problem, S3CS3, is reversing the input string. If you understood how to determine if the given input string in particular, or if a given input array in general is a palindrome or not, using the notion of two runners which advance or which traverse the input container from two opposite extremities and move towards the perceived vertical axis of symmetry of that container one step at a time and in unison, then you will have no problem constructing an algorithm for reversing an input string or for reversing an input array, for example, using the same idea. That is, this time, as you saw in the opening image for this segment, we also introduce two runners. The left runner that is positioned at the beginning of the input array of the input string, and we introduce the right runner who is positioned at the rightmost extremity of the input array at the position n-1 in the given array. And again, the left runner advances rightward once, and the right runner advances leftward once through the container. Both of the runners move towards the logical vertical axis of symmetry of the given input string or the given input array, regardless of the parity of the size of the string or the size of the array, even or odd. And the condition for the termination of our algorithm, just as the condition we saw for the termination of the previous algorithm, the algorithm for the detection whether the input string or input array is a palindrome or not, we do so as long as the left runner and the right runner did not overlap or did not crisscross their positions. Here, however, in the previous image, I put the radios or walkie-talkies for the two runners. In this image, for the algorithm that will reverse the input string, I put the slingshots for our runners, because at this time the runners don't really have to communicate. All they have to do is act. They have to throw or launch, let's say, whatever character they see at their current position toward the opposite runner. And in this case, we do not really have to have any if statements within the body of the loop. All we have to do is technically swap the characters at which positions? At the positions that are equidistant from the logical or perceived vertical symmetry of the input string as such. Our algorithm doesn't really have to return anything in general. That is why you see void reverse string on the input. This time we will be modifying the input container, input string in place, thus honoring the big O01 space complexity of our algorithm, which is exactly what we're required to honor in the original problem S3C-S3. And then the second argument is n, which is the size of the input string. In general, again, this is tribal knowledge in C. The size of the string can be controlled. We can, as a caller of this function, we can step inside the string and cut it off from the big some amount of space into that string, move the pointer to somewhere within the string, and then say reverse only that portion of the string. It doesn't have to be the entire length of the string. It has to be some number. So this is the flexibility we built in. The number of characters to reverse and starting from here. Notice that there is no const keyword over here because we will be modifying this container in place. There is no constant. We need to modify it. Now we position our left runner. This time you can implement this algorithm using the indexes like I did in the previous segment, but this time for me it's personally more natural to operate in terms of pointers too. And in this case we have character pointers to the elements in the array. Again, the left runner, this usual suspect, is initialized to point at the address of the first element in the string. This is more explicit syntax that communicates the idea that was in the mind of the author, and then it is left there, so when the other person looks at it, they understand what was happening in the mind of the person who wrote this code. The right runner is initialized to point at the address of the last element in the input array, s sub n minus 1. And then we fall through into the for loop where we do not need to initialize anything. We do not really need to do anything after. We could, but we do it in the body. We could do it over here. The condition of this loop is pretty much essentially fundamentally exactly the same as the condition for the algorithm termination in the previous case in the palindrome. Remember that we traverse our input container from two sides using two runners, and the two runners move which way? They move in unison. So here this idea is again encoded over here. We will talk about it in a second. But once we observe that, again, in the opening segment, the image you saw that our runners had the walkie-talkies to communicate. They did not really take any action. In this algorithm, there is no need to communicate. We only need to take action. And these three lines of code encode the swap. So logically, this is the swap. This is the swap of characters, which I portrayed over here. The character A, let's say, for example, in this case, is flying over the string into the position and dropped into the position where the character D was, and the character D is yanked out, flies across the string, boom, and dropped into the position where the character A used to be. So after the first iteration, what we'll have D, B and C will still be where they are, and then there will be A. This is iteration 1. We save the contents of whatever, let's say, the left runner points to in the temporary variable. This is the frame variable created on the frame of this function. Then when this function returns, all the frame variables are gone. Then we write into the position which is pointed at by the left runner the contents of whatever the right runner sees right now. This is captured in this line of code over here. A star in front of the pointer, the so-called dereference. So step into this address, grab what the address points to, copy it into the location pointed to by the left runner. So at this point, the contents of whatever the left runner points to have been erased. And at this point, for example, the string will look as follows. It will look as follows: D, B, C, and D. So this is the temporary effect at this line of code. Now here at this line of code, right here, we take what we saved from what the left runner saw in the variable called temp, the frame variable here. No need to allocate it, just move the frame stack pointer and copy that contents into the address location pointed at by the right runner, which is this location right here. So after this line of code executes, now we will have D, B, C, A, and the reversal of the string is already in progress. Here, the next step is what? The left runner, remember, the left runner moves towards the logical or perceived end of the string rightward, and the right runner moves towards in the opposite direction, towards the perceived or logical beginning of the string leftward. So the left runner moves right, the right runner moves excuse me, left into this position, and here the swap repeats again. B goes into C, C goes into B. After these two lines, the loop jumps at the beginning, the condition is tested, the left runner did not crisscross its position with the right runner, everything is good, we fall through, we swap the characters, we advance the positions. At this point, this test will fail, the loop will terminate, and the output we will have precisely the following: B, C, B, A. At this point right here, when the function returns, this is what we will have in our container. But again, fundamentally, essentially, it is important to understand that the algorithmically beautiful idea that is reusable in several places, in several contexts, is to introduce two runners and to traverse the input container, in this case from two opposite directions towards each other. The runners will collide in the middle, and this collision in the middle is the condition for the termination of the algorithm. This is when the algorithm terminates. And what is the characteristic feature of this algorithm and the previous one? This is the question that is addressed to this line of code. Mathematically, what does it mean, and in computer sciencey way too? Well, mathematically and in the computer sciencey way, these two lines look quite innocent, but actually they carry quite a lot of weight. Remember, in at the end of season 2, we studied what? We studied the problem-solving approach in mathematics called invariant. So in these two algorithms, we have an implicit invariant that I did not, again, spell out explicitly. It is there implicitly. So what is it? The implicit invariant in both of the algorithms that we looked at in the previous segment and in this segment is the symmetry of the elements of the input container that are being acted on. And the symmetry is evaluated with respect to the logical or geometrical vertical axis of symmetry of the input container. This is an important thing. This is the built-in implicit invariant in both of the algorithms, and it is captured over here. In other words, both of our runners advance through the input container at the same speed, or they advance in unison. If the left runner moves forward, so to speak, one position in the array at the consequent iteration, then the right runner moves in its frame of reference forward, or it moves, in this case, leftward, one position also. This is encoded over here. And for those who are not familiar with C, I will say that these are the ways for the compiler to generate the correct code. For example, if our array is of characters, then the compiler will generate the code to move these pointers by size of char. If our input array was, for example, the array of integers, then the compiler will move the pointers not by usually traditionally one size of char, but by size of int, which on many modern computers is, let's say, 4 bytes and so on. But fundamentally and essentially, the takeaway from this algorithm and the previous one, two runners, they move at the same speed, they advance in their respective mutually opposite directions toward the middle of the input container in unison at the same speed. And this is the condition for the termination of the algorithm, when in plain English the position of the left runner and the right runner crisscross, and at that point we terminate our algorithms either way, for detecting whether the input string is a palindrome or for reversing the string. Now that you understand how these two tasks can be carried out using the notion of two runners, think about how you will solve the actual problem that we're trying to solve in this episode, S3CS3. If by now you understand how an input array can be determined to be a palindrome or not, or how a string can be reversed using the idea of two runners chewing on the input container from two um, diametrically opposite extremities and moving through this container into two diametrically opposite directions toward each other, then you should be able to put the sought after algorithm for sorting the given input array in such a way that all the zeros in this input array gravitate toward the left extremity of this array, and all the ones gravitate towards the right side of the input array, and thus implement the so-called single pass Janus sort. Again, if you have a better name for this sorting algorithm, by all means share it with us in the comment section. Now here, one little caveat that we need to discuss before we jump into the mechanics of this algorithm is the following. We will take that all the objects or all the elements of the input array of the same type, all the zeros, are indistinguishable, and all ones are indistinguishable as well. As such, the position of the specific zero within the sorted array, we take it to be not that important. And likewise, the position of this specific one in the sorted array is not that important. Technically, in the language of mathematics, what we have here is the so-called multi-set, or a structure which allows for duplicates. And usually in mathematics, every element in a multi-set carries another characteristic attached to it, is the multiplicity count. So here we need to sort this indistinguishable across the same type of elements array into two piles. One such pile contains only objects of one type, and the other such pile contains the elements and nothing but and only the elements of the other remaining type. Here again, we do the same thing. We introduce two runners, the left runner and the right runner. The left runner and the right runner. The left runner will advance through the input container rightward towards the perceived or logical end of this container, and the right runner will start at the rightmost position in the container and move leftward towards the perceived beginning of the container, and we do so with these lines of code. The left runner is the integer pointer, the frame variable that is clocked with address of the very first element in the input array. And because we will be changing the contents of this array in place, honoring the space complexity of one requirement of this algorithm, there is no const qualifier. And size dn, this is basically a non-negative integral quantity 0, 1, 2, 3, and so on. N is the size of the input array. So as such, we initialize the frame variable called left runner, pointer to an integer, with the address of the first element of the input array. Likewise, we initialize the frame variable called right runner with the address of the last element in the array. And as a side effect, we also introduce another frame variable of type size t. I call it x, initialize it to 0. It will keep track of the number of swaps that we perform in the upcoming algorithm. Again, overall, we wrap our algorithm into a for loop with the condition that the address of the left runner is strictly smaller than the address of the right runner. In other words, the addresses or the positions of the left runner and the right runner do not crisscross. And the moment they do, this is the termination point in our algorithm, which is guaranteed to work if we couple it with this condition right here, but we will get to it in a second. As such, the first thing we do, we want to test that what the left runner sees is not 0 and what the right runner sees is not 1. Capturing it, this test this way, we emphasize the idea that the left runner likes or wants to see only the objects that's supposed to gravitate as the result of the sort to the left side of the container. And that is what? That is zeros. And the right runner wants to see only the objects that's supposed to gravitate towards the other extremity of the input container. And that is what? That is ones. So here we can see the way I constructed this test is that whatever the left runner sees is not 0, and whatever the right runner sees is not 1. Technically, again, we can construct these tests in the other way. For example, we can say if the left runner sees exactly 1 and the right runner sees exactly 0, then we do the swap. Otherwise, we determine whether we advance through the input container in either direction. But I think that the idea that the person had in mind when he wrote the code, by the time the code is written, checked in, compiled, tested, installed into production, and everyone forgets about it. 6 years later, someone comes in, looks at it. That idea, of course, is gone from the code, but the intention or the idea that was in the mind of the person who wrote the code is there. This way, I think it is more clear which type of object is supposed to be on which side of the container. If we say that the left runner does not like seeing zeros, that means that precisely 0 is supposed to be on the left. And if we say that the right runner does not like seeing not ones, then that means that the one's supposed to be on the right. If the left runner sees not zeros, then that's not good. He wants to see zeros. If the right runner sees not ones, that's also no good. It wants to see only ones. And if this happens, this is captured with the AND, and sometimes students miss that. This condition has to be satisfied on both ends. And if what the left runner sees is not 0 and what the right runner sees is not 1, then we perform a swap. The swap is shown over here. And here, the first thing that we do, we also keep track of the number of swaps that we have performed, x plus plus. And the way we do the swaps is as follows. We take the contents or whatever the left runner sees right now, store it in the frame variable called temp. Then we overwrite the memory location pointed to by the left runner with the contents of the memory location pointed at by the right runner. And since this location is gone, we want to override the location pointed at by the right runner, but what we stored in temp. The temp, again, is the integer. Now that we have performed this swap, if needed, we decide whether our runners advance through the container. This is how we do it. If the left runner right now, after the test and swap if needed operation, sees exactly what it likes seeing, that is zeros, and again, this echoes what we do over here. the left runner does not like seeing not zeros when it runs through the container. So if it sees the 0 after test and swap, then it will advance one step which way? Rightward towards the perceived end of the input container. Likewise, if the right runner after the test and swap if needed operation sees exactly 1, what it likes to see, which should again echo with this test over here where we say that the right runner does not like seeing not once on its run through the container here, then the right runner advances in its frame of reference forward, but in our view it advances which way? Leftward once, rightward once, and thus we roll through the loop again and again and again, and the combination of two things will ensure that our algorithm terminates. The address of the left runner is smaller or less than the address of the right runner. Remember, the addressing grows in the array however the memory is laid out, and then our left runner address grows potentially and the right runner address diminishes. So the two runners potentially approach each other, and the moment they crisscross, the algorithm terminates, and this will work either way. For example, let's say all the elements in the input array are all zeros, then what will happen? Well, the left runner will always see zeros. It will keep stepping forward or rightward and rightward, but the right runner will never see a single one. This test will never succeed. It will always fail. So the right runner pointer will be sitting at the last location in the array at all times, but the fact that the left runner will increment, it will eventually catch up and run over the right runner. Likewise, if the input array contains nothing but ones, then again, the left runner will never see any zeros, it will never advance, but the right runner will work its way towards the beginning of the array, and again here, the right runner will overrun the left runner, and this condition will kick in and the algorithm will terminate. And I captured this in this little schematic. If after the test and swap if needed operation we see these conditions, then our runners advance. And let's say over here we see that the left runner detects a not zero, which is 1. Left runner detects not 0, which is 1, and the right runner detects not 1, which is 0. The right runner detects 0. Then these two entries are swapped. 0 goes to where 1 used to be, and 1 goes where 0 used to be. And then after that swap, we will have 0 in this position, 1 in this position, and again, the left runner will step rightward once with the plus plus, and the right runner will step leftward once with the minus minus, and the whole for loop and test and swap if needed operation will repeat. And at the end, when the loop terminates, at some point this will happen. The size of our input array is finite. One address may grow, the other one only may decrease. So at some point these addresses will crisscross. So this test in combination with this operations that we do guarantees that the algorithm terminates, and we return what? We return the number of swaps that we performed. Every time we perform a swap, we increment it by 1, and this is what we return. Sort zeros and ones. This is the implementation of this algorithm. Now that you understand how the theory works, let us see how that algorithm will look like in practice as we run through a sample sort. And now for demonstration purposes, let us assume that circles behind me represent zeros and squares represent ones, and we need to apply our single pass space complexity big O of 1 Janus sort to this particular array of elements and make sure that all the circles at the end of that sort gravitate towards the left of the array and all the squares gravitate towards the right of the array. So let us play out our algorithm that I did not erase and I left it here, and when we do so we will notice that our left and right runners move which way? They move independently this time in this algorithm. Recall that in the palindrome detection algorithm and string reversal algorithm, both runners moved at the same speed, or they moved in unison or symmetrically with respect to the vertical axis of the input container. Here, in this particular algorithm, this is not the case. Our left and right runners move at varying speeds, and we will see that right now. As such, our left runner right now points to this, to the contents of the leftmost, the first element in the array, and our right runner points to the rightmost, or the very last element in the array. We initialized our left and right runners, and now we run the test. Is it the case that the left runner does not see a circle? Does not see a circle? Yes. So that part of this compound and statement is true. But is it the case that the right runner sees not square? This is not the case. False. True and false is false. The test fails. We do not do any swaps. We come over here. We now do the test. Is it the case that the left runner sees a circle? That's not the case. So the left runner stays where it is. Is it the case that the right runner sees a square? Yes, it is the case. The right runner sees a square. Wonderful. We minus this pointer, and now the right runner points this way. The left runner is still to the left of the right runner according to this test. Their positions did not crisscross. We fall through to another iteration. So is it the case that what the left runner sees is not a circle? Yes, it is true. Is it the case that the right runner sees not a square? Yes, it is true. Boom. On this iteration, we step into the swapping territory. So we swap our elements. This circle and this square exchange their places like so. And after that exchange took place, we go into the advancement territory, and we want to see if either runner advances. Is it the case that the left runner points to a circle? Yes, it is the case. We advance this runner, so the left runner points this way. Is it the case that the right runner points to a square? It is the case. So we advance this runner also, but this one, carefully notice that the left runner advances rightward and the right runner advances leftward, and the whole thing repeats. Our algorithm termination case did not fire. It's still, the test is false. We're still far apart. We run the test. Is it the case that what the left runner sees is not a zero? No. Or a circle? No, it's not the case. Is it the case that the right runner sees a not square? It is the case, but we have false and true evaluates to false, no swaps. We come over here and we see if the left runner points to a circle. Is it the case? Yes, it is. So the left runner moves forward, rightward, steps rightward once. Is it the case that the right runner points to a square? No, the right runner stays where it is. Iterate in the for loop, test the condition. The condition is good. Is the left runner points to a not circle? No, this is false. and the right runner points to a not square. This is true, false, and true evaluates to false. No swaps. Is the left runner pointing to the circle? Yes, it is. We advance the left runner once over here. What about the right runner? Does the right runner point to a square? No, it does not. Keep them where it is. Iterate, test succeeds. Do we do the swap over here? Evidently, we do the swap because the left runner right now sees precisely not 0, which is a square, and the right runner sees not a square, precisely a circle. So now there is another swap. We record it. We swap our elements, and we work on the advancement. Do our runners advance? And in this case, they evidently do. The left runner points to a circle, and the right runner points to a square. So now the left runner moves rightward once carefully over here, and the right runner moves leftward once carefully over here. Next, does the algorithm termination condition fire? No, it does not. Our runners are far apart. There is no crisscross in memory. Now we do the test. The left runner points to a not circle. True. The right runner points to a not square. False. True and false evaluates to false. No swap. We do the test. Is it the case that the left runner points to a circle? Nope. Is it the case that the right runner points to a square? Yep. So we move the right runner leftward once over here, but the left runner stays where it was. The loop comes to an end, jumps back in, the condition is tested, it fires as true. We come here, we do the test. Is the left runner positioned against the not circle? It is true, yes it is. Is the right runner positioned against not square? Yes, it's true. What do? We do a swap. So the circle goes where the square used to be, the square goes where the circle used to be. Now, what about the advancement? The left runner is advanced because it points to a circle, carefully over here, and the right runner is advanced leftward because it points to a square. There is no crisscross in memory. The condition still holds. The left runner points to a not circle. This is true. The right runner points to a not square. Is it true? This is not true. True and false evaluates to false. No swaps. What about the advancement? The left runner is supposed to point to where? To a circle. Is it? No, it does not. So the left runner stays put. What about the right runner? Is it the case that the right runner points to a square? It is the case. So what do? We advance him in his reference frame forward, but for us it's leftward once. So now the right runner points into the same memory location. So right here we at this point in the loop, then we come over here, jump over here, the test is executed. Is it the case that the left runner is strictly to the left of the right runner? No, it is not the case. Actually, in memory, these two pointers point to one and the same location. Boom, the algorithm terminates and we return. At this point, our array is sorted. Is it sorted? Yes, it is. All the circles are on the left. All the squares are on the right. There are no intervening squares, or there are no intervening non-circles on the left. There are no intervening circles or non-squares on the right. Problem solved. You saw the algorithm in action. And here there are a number of questions can be asked. For example, this will be an informal and fun homework assignment to our viewers who like to play with these things. Think about this. Is this algorithm stable or not? In other words, will it move or will it not move the squares and or circles when it doesn't really have to do it? And the answer to this question, it seems to be no, this algorithm is not stable. It can so happen that even though it didn't have to move certain elements, it will still move them around. So think about the following question. Is it possible to make this algorithm stable but the still honor the constraints that we imposed on this algorithm first? Also, don't forget that hopefully you saw in this mechanical demonstration, you saw the fact that the motion of the left and the right runners was independent. They moved at different rates of speed. So is it possible to make this algorithm stable still, having it a single pass and big O of 1 in terms of space complexity? Is it possible? What do you think? And if it's possible, then we would like to hear from you and see your implementation of this algorithm. But in any case, I hope that this demonstration justifies my choice for the name of this sort, Janus sort. Imagine two faces. One face looks this way because here nothing but squares. The other face looks this way because here there's nothing but zeros. This is my arbitrary choice. Again, if you have a better idea, then by all means share your better idea with us for the name of this algorithm. Now, if you understood the ideas behind the construction of this algorithm, our next computer science problem will be not the next challenge. The next challenge will be a couple challenges in math. It will be problem in physics, and then eventually problem in computer science. But the next computer science problem, S3CS4, will be the following. Let's say we have a linked list. And then it so happened that through not so careful manipulation, the one of the nodes in that list somehow points to, instead of pointing to the truly correct node in the list, this link has been severed due to not so careful handling of the pointers. Now this guy instead points to this element right here. So what we now have is called a cycle. And if we have more elements over here, most likely this is a memory leak. This breakage of the list constitutes a memory leak. You will never see this memory again. You will never find it. If you have a pointer to the head of the list, this, for example, will be your head. If you have a pointer to the tail of the list, let's say if you can afford in memory budget to keep the pointer to a tail, you will have pointer to here. If your linked list is singly linked, then you're pretty much dead in the water. This node is lost forever. It's a memory leak. If you have a doubly linked list, maybe you can somehow recover this memory. But anyway, the point is this. Using the ideas that we developed in this episode, construct an algorithm for detecting whether there is a cycle in a misshaped linked list that was handled not carefully or not. Again, I will present my solution of this problem when the time comes to it, but now as a heads up, you have something to think about, and perhaps you will be able to solve this problem using the ideas that we developed in this episode. And it doesn't really sound as artificial as it may at first blush. For example, in my professional career, I spend most of my time working on the so-called real-time applications or ultra-low latency, where every literally millisecond or perhaps even at some point microsecond counts. The code has to be as performant as possible, very, very fast. And what we do in these cases, we allocate all the memory at the program startup, and we do not do mallocs and freeze during the actual program run in stable state. So in the real-time path, there is no mallocs and there are no freeze. So all the nodes, of course, are not linked in any way. There is no way to meaningfully link them. So what we do is we allocate some number of nodes at startup once, and we call this list, for example, a free store. From this free store, we grab nodes as they a request for them comes in, and we construct a linked list from these nodes. And when the lifetime of the node is over, someone says remove this node from the list. I will grab this node and put it back into the free store, return it to the free store. Eventually, over the lifetime of the program, of course, what will happen? Well, if we have doubly linked list, of course, or maybe sometimes there are more complicated structures where we can point to one over, like so. Also, for whatever reason, it becomes very error-prone situation to handle these links, previous, next, or whatever, very correctly. And if you fail to do so, it may very well happen that if you, for example, forgot to clear certain pointer, then it is actually quite likely that you will have a cycle, and you will erroneously inject a node into your list where one of the pointers hasn't been cleared, and it points to the previously from the leftover, the address from was left over from the previous allocation. Dole it out, use it, come back, did not recycle it properly, get it allocated again, and boom, you have a cycle. Bottom line, the question in the next computer science problem will be design an algorithm that will detect a cycle in a perhaps not so carefully handled linked list. And now this is it for the computer science problem S3CS3, and we will move on to a new challenge next. Before I formulate our next challenge, which will be a problem in mathematics, the problem S3M9, I would like to say that at this day and age, there exists a certain collection of problems that live, again, this is just my terminology, my idea, that live on the great international mathematical grapevine. These problems, basically internationally known problems, are usually they are of an exquisite mathematical beauty. And among these problems, the problems that live on the great international mathematical grapevine, there is its own class of problems, which again I call the amazing problems. So some amazing problems live within the set of problems that live on the great international mathematical grapevine. And my definition of an amazing problem is that a problem is amazing. Usually it's a problem that comes off of the great international mathematical grapevine, but more importantly, such a problem has the following property. Every time we look at it, we generate a new and sometimes quite distinct solution that is different from all the solutions that were generated previously. I've been dealing with some number of these amazing problems. We will look at some of them, and every time I look at such a problem, I invent a new solution, and it never ceases to amaze me that how this is even possible. So one such problem that actually comes from the great international mathematical grapevine. Okay, here is the small nuance again, in my humble, not professional, and evidently arbitrary opinion. It is not the case that every problem that lives on the great international mathematical grapevine is an amazing problem. Some such problems, no matter how exquisitely beautiful they are, they admit pretty much one solution and one way to solve this problem. And we actually looked at one such problem that lives on the international mathematical grapevine. We looked at it in season 1, episode 6. Season 1, episode 6, I wrote it on the bottom over here. That was the mathematical problem S1M5. We took a regular tetrahedron. Here I have a paper model that is made out of pieces of paper that have different color. And then the question was, how do we traverse this regular tetrahedron in the shortest possible way? And then in the problem S1 and 5, we actually proved that such a regular tetrahedron can be traversed over its outer surface in a way that that path is shortest among all paths possible, that lies through actually the dead middles of each edge. And once we connect this middles through the edges, then we get this circumnavigating path of shortest length. And amazingly enough, not only that, but this particular path, the shortest by length circumnavigating path through a regular tetrahedron, also cuts our solid into volumes of equal magnitude, actually. And once you look at the two pieces shown separately, it's not really clear what they are, but again, amazingly enough, if we put them together, they come down and become a regular tetrahedron. Quite amazing thing. So this problem definitely lives on the great international mathematical grapevine. I wouldn't call it necessarily an amazing problem, but it is still quite beautiful, quite exquisite. Now, this problem that will be S3E15, this is a typical example of a really amazing problem. It does live on the great international mathematical grapevine. It is of an exquisite mathematical beauty all by itself, in isolation from everything. And on top of that, and in addition to, it is an amazing problem because every time you look at it, you invent a new solution. And this is what we invite you to do. So the problem S3E9 is the following. Given three distinct parallel straight lines that belong to one plane, I should probably say three distinct. Over here, they must be coplanar. They all belong in one plane. Then, using the Euclidean tools alone, a compass and a straight edge, you are to construct, invent, synthesize, put together, discover an algorithm according to which, with the Euclidean tools alone, it is possible to construct an equilateral triangle on these three parallels, meaning that the three vertices of this equilateral triangle live precisely on the given straight lines, one vertex per straight line. So in high tongue, we need to come up with the bijection. Each line carries one vertex, and each vertex goes back to precisely one straight line. Let's name them L1, L2, L3, all in one plane, parallel. Again, using the Euclidean tools alone, construct an equilateral triangle in such a way that the vertices of this triangle all sit on these three distinct parallel straight lines. And once you solve this problem, I highly recommend, to put this problem aside, give it a week or two, a month or two, come back to it again and find yet another solution of this problem. In the next episode, I will share three solutions of this problem that I can think of, but again, I'm absolutely sure that there are way more ways to solve this problem, as I will share with you, but this will be just a conversation starter. Now, this is it for the episode S3E15, and thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share three solutions of the mathematical problem S3E9.